So far we have seen array multiplier, but the problem with array multiplier is it was multiplying things spatially. That means we have lot of partial products in every row, correct? So rather than that, what this sequential multiplier does is, so it is going to do addition. That means it is going to maintain one copy of partial products. If new partial product comes, it will be added to the old partial product. Now we will see the process using the example. Okay, so here first of all, we'll see simple multiplication so that you can understand this process. First, what we do is we assume that we have a initial partial product 0, 0, 0, 0. Okay. Now, whenever you see this bit, we are going to do what? Definitely, we are going to add 1, 1, 0, 1. If the bit is 0, then we are adding 0, 0, 0, 0. That is a process. By this time, you have already understood that, right? Now, the first step is adding 1, 1, 0, 1. Once you add 1101, you get what? 1011. For cross-checking purpose, first of all, we'll see the values. This is actually 13, and I'm assuming again it is, positive numbers. That means unsigned numbers. So 13 into 11, which is nothing but 143. We should get 143. Let's cross-check. So once addition is done because of this bit, what we have to do? We have to, use this bit and we have to multiply. You get 1101, but we should not add 1101 here. We know that, right? We have to add 1101 here. That is equivalent to saying that this our 1101 should be shifted left side. Otherwise, this 1101 should be shifted right side. One of them should happen. So that's why what I do is I will shift 1101 right side in implementation. Here it's a paper and pen calculation. So if I write 1101 here, that would be sufficient. Remember one thing, this is the way we add, you know that, right? This is in circuits is nothing but previous result. This is some result, right? The previous result is right shifted, then after that we added 1101. Remember it. So there is a shift operation, correct? Remember that. So here 1 and 1 and 1 you are getting. So here 1 plus 1 0, then here 1, 1 plus 1 0 and 1. Assume that we have this much space in our registers, then only we can store this new result. Okay, now this is your new result, right? New result. So we will not be maintaining, sir. Here also we have 1101, right? So that 1101 and this 1101 will be added and that will be stored in the old copy only. That's why we will be maintaining only one copy. Don't worry. I will show with the example. First we are focusing here how calculations take place. Then after that 0. Before that, you know one thing. This 0000 to be added here, correct? That means what? Previous time we added 1101 here, right? In these positions. If you see the positions, then we added 1101 here, but this time 0000 little bit left side. For that, in implementation we have to do again shift. Okay, so here shift will happen, remember it. After that we add 000. So that's why when you add 0000, that means in our circuits we have to shift this 100111. So 1 1 1 0 0 1. See, though you are not understanding that shifting is happening, but you have to feel it. See, here you have 1101, then 1101 is added here. If I assume that, let's say these 4 bits are some bits in the register, we have a register 1101, then we are not adding 1101 directly to this 1101. After shifting this 1101 we are adding. Similarly here also we are not adding 0000 in the position of 1101. That's why it is called shifting it again right side. So you get 100,111. Now after that what we have to do? Again we have to add 1, right? So we have to multiply with 1. That means you get 1101. See, previous time you added 0000 here. This time we have to shift it. 100,111 should be shifted, right? Now you can clearly understand. So I am going to add 1101 here. That means what? Previous time 100111 is added to 0000 in these 4 positions. That means effectively 1001 is added to 0000. But this time 1001 is not added to 1101. But that means what? So we will be shifting 100111 to right side. Remember it. So that's why you get what? 1 1 1 1 0, 1 plus 1, 0, 1 plus 1, 0, then you get carry. Okay. So this is the way we do. So I assume that let's say still I have, let's say, some more bits. If I have some more bits, I do shifting, so that if I shift, then next operation will be convenient, correct? Every time whenever you want to do the next operation, we have to shift the bits. Okay. So in that way we can of course shift the bits, not a problem. At this moment, what is the answer? If you see 2 power 0, 2 power 1, 2 square, 2 cube. If you see 1 1 1 1, the meaning of 1 1 1 1 is 15, right? The value. This 2 power 5, 2 power 6, 2 power 7, 2 power 8, 2 power 8, sorry, 0, 1, 2, 3, 4, 5, 6, 7, 2 power 7. So 128. 128 plus 15, 143. Yes, it is correct. So this is the operation we are going to do here now. Don't worry. So how to get the feel of shift, I will tell you. But you remember that there are shift and addition operations. The entire process is nothing but shifting and adding. So what are you adding? Either 1101, otherwise all zeros. So if the current bit is 1, then we add 1101. If the current bit is 0, then we add all zeros, right? Let us do it with now the registers. That means now we have equipment. What is the equipment we are going to take? We will see. Now we will be taking one flip-flop called C. Okay, flip-flop is nothing but a memory element which can store one bit of information. Now we will be having a register called M, okay, that is multiplicand, and we will be having one register called multiplier, let's call Q. Okay, so Q contains 4 bits, multiplicand also 4 bits, 4 plus 4, 8 bits. Now this A is nothing but a temporary register which is going to store your result, right? Sir, with 4 bits, how can you store the value? I will tell you. So example, you have 2 bits of information. Okay, you are multiplying 2 bit numbers. How much space you require? We'll just observe. 1 1 means 3. This 1 1 means 3. 3 3 is a 9, right? So to represent 9, you need 1001. 4 bits are required. Similarly, let's observe for 3 bits. Why I am taking 111? I will tell you. This is a maximum number representable with 3 bits, right? I am assuming unsigned numbers. So here also 111 is highest number. If I multiply these two highest numbers, that will be, then the result is the maximum number possible in multiplications, right? So 7 7 is a 49. No one can get better than 49 by multiplying two 3-digit numbers, so especially binary numbers. So 49 is nothing but 32, 16, 48 plus 001. So 11001, I think 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. It's not 11001, 11001. See, 0, 1, 2, 3, 4, 5, 32, 16, 48 plus 1, 49. That means how many bits are required? 3 plus 3, 6. Similarly, you can observe for some, 4 bits, 5 bits, and slowly you realize that for multiplying two n-bit numbers, you require 2 n bits for sure. We can't reduce it, okay? 2 n bits in the worst case. That's why we should be prepared for that. Now I'll give you just a rough idea, not exact idea, but why we require 2 n bits, I will tell you. With n bits, the maximum number representable is 2 to the power of n minus 1. With this n bits also 2 to the power of n minus 1, almost 2 power n, remember it, right? Similarly, here also 2 power n minus 1 is nothing but 2 to the power of 2n, correct? Then if you multiply 2 to the power of 2n into 2 to the power of, 2 power n and 2 power n, if you multiply these numbers, the result is going to be 2 to the power of n into 2 to the power of n, which is nothing but 2 to the power of 2n, okay? But not exactly 2 to the power of 2n, approximately 2 to the power of 2n. Then it is, less than definitely 2 to the power of 2n. Now remember one thing, to represent a number called 2 power n minus 1, we require n bits. The formula for that is 2 to the power of n minus 1 plus, 2 power n minus 1 plus 1 log base 2. Okay. Whenever you want to know the number of bits required for binary numbers to represent some number is log that number plus 1 base 2. Okay. So here it would be log of 2 to the power of n base 2, which is n, right? That means that's why n bits are required to store 2 to the power of n minus 1. So similarly here also we have a number approximately 2 to the power of 2n minus something, 2, 3 something, let's say. Okay. because we did not take exact values, right? If you take exact values, then it would be 2 to the power of 2n. Let's multiply them. If I multiply them, you get 2 to the power of 2n. So you know how to multiply. 2 to the power of n minus 1 into 2 to the power of n minus 1. If I do simplification, you get 2 to the power of 2n, this one and this one, minus, so a minus b whole square, a square minus 2ab, 2ab, ab, a is 2 power n, b is 1 plus b square, 1 square. So it would be 2 to the power of 2n minus 2 to the power of n plus 1 plus 1. So it is approximately, definitely, this value is definitely greater than, sorry, this value is less than 2 to the power of 2n minus 1. Do you agree? Yes. So to represent, a number which is less than 2 to the power of 2n minus 1, 2n bits are sufficient. Same formula I can apply. Log, right, approximately 2 to the power of 2n minus 1 plus 1 base 2. That would be log 2 power 2n base 2, which is nothing but 2n, right? So with 2n bits, definitely I can represent any number less than 2 to the power of 2n minus 1. I know that already. Now we know that we have definitely less than 2 to the power of 2n minus 1 numbers, because what is the maximum number we have? 2 to the power of 2n minus 2 to the power of n plus 1 plus 1. That's why 2n bits are sufficient. Sometimes we require 2n also. So just remember it. So these two things always you should remember. To multiply two n bit numbers, we require 2n bits. To add two n bit numbers, we require n plus 1 bits. Okay, because you get end around carry, to represent that you require one more bit. That's it. Now that's why what I am going to do is I am going to store the result in these 4 bits, because when you multiply m and q, 4 bits, you get 8 bits, right? That 8 bits I am representing, 4 here, remaining 4 here. Sir, but remaining 4 are already occupied, right? Yes. But when you are doing the multiplication process, after some time, so this bit will be unnecessary. I don't want it, right? At that time, in this place I will be storing. Okay, after that this bit will be useless, then I will use this space. Eventually all these bits become useless once operations are completed. That's why effectively we can use, you just observe the process. The first step, if you see, we have 0 0 0 0. Yes, even we have here 0 0 0 0, right? Now then immediately what we did is, because the value is 1, right, then we have directly added. The first step we did is add, correct? So here also how to imitate this multiplication procedure is, so we have to connect one circuit to this bit always. Okay, this bit should be connected to one decision circuit. That decision circuit should do two things. Okay, the actions of that decision circuit like this: by seeing the input of 1, it should do action number 1, either add 1101, otherwise add 00000. Correct? These two things we are always doing based on this bit, right? If since this bit is 1, then we will be doing this one. If the bit is 0, then we will be adding all zeros. Adding all zeros is nothing but don't do anything, because save the time, correct? So that's why. So rather than adding 4 zeros, just keep quiet, correct? So that one addition time delay we can reduce. Remember it. So the first step, now always we will be observing this bit. Okay, now since this bit is 1, we have to add 1101. Already we have that in multiplier. Now I am going to use an adder circuit. So for that adder circuit, which is a 4-bit adder, sir, yes, I agree that it is 4-bit adder, but are you adding using carrier look ahead adder? Otherwise simple adder, anything is fine. Finally that should be adder. Okay, so you can implement in any way. Implementation details are unnecessary. Now what I am going to do is, I am going to connect that 4 bits m here. I am going to connect this a here. Then I am going to add them. When you add them, you get 5 bits. We know that, right? 1 2 3 4 5. This 4 I am going to store back to a again. Okay, that means these 4 bits are connected back to this register. This bit is connected to C. That's why once addition is done, the result will go to C comma A. Okay, let us see that. Now here, The first step, since this bit is 1, there is a decision circuit. Already I told you that decision circuit enables adder. Okay, so when adder is enabled, then 1101 will be automatically added to 0000. Such a way we have to connect these two, add these two to adder. Okay, now you get what? 1 0 1 plus 0 1. Sorry, yeah, correct, it is 0, right? 1 plus 0 1, you get 1101. What is the carry? 0 you get, right? In adder there is no end around carry, that is 0. So let's transfer. 0 will go here and 110 I write here. Okay, so this is because of the result called add, right? So after adding, 0 comes here. All these values I am showing here because they got modified, right? So I am writing here 0 1 1 0 1. They supposed to be written here, but for understanding easily, but to see easily, I am writing here so that you can see previous version, new version, but there will be only one version. Okay, so now at this moment the contents of the C comma A are actually 0 1 1 0 1 after doing add operation, right? Then 1 0 1 1. Now this bit is useless, right? Its operation is done. Then we are going to use shift now. Why shift? You see here, once you get 1101 into the result, then next time we have to add the next addition after doing the shift operation. That's why immediately we have to do shift. Remember one thing. So in the entire multiplication process, once addition is done, immediately we have to shift, right? That's why there should be a shift operation. Let us try to understand how shift happens. So shift right we have to do. Okay, so shift right is like this. This bit will be disappeared. We are losing this bit. In this place this will come, in this place this will come, such a way. So these are all registers, correct? So registers can be implemented as shift registers. That means, in an example, let's say you have a shift register. Okay, 1101, simple shift register. Okay, then we can use this shift register and we can implement an operation called right shift. Whenever right shift is done for this shift register, then so this 1 will go this side, this 0 will come here, this 1 will come here, this 1 will come here. In the empty place, either you can make 0, otherwise 1, depends on your logic. Anything we can implement. Let's, for our purpose, actually we need to fill 0. Okay, so this is called right shift. When you have a register, then we can implement an operation called right shift operation. Okay, for that you will be having extra circuit that you will be studying in digital, not here. Okay, at this moment we are assuming that a register can be shifted, right? So right shift. Now I am doing that. This is a register, this is a register, and this is a flip-flop, this is a register. Let me do right shift. So this, all these registers connected to that shift circuit. So because of that it will be shifted. Let us do that. So when I do that, already I told you what happens. This 1 will be disappeared. So this 1 will come here. Okay, that means this 1 comes here, this 1 here, this 0 comes here, then this 1 comes here, this 1 comes here. This is shift operation. So what about this place? This place will be occupied by the left component 0. Here 1, here 1. See, like this. Okay, next like this 0. So 0 1 1 0 comes here. Then here, sir, what about this position? Because we are doing right shift by through 0, we say. Okay, we can do right shift through 1 also. That means the last position will be either filled by 1 or 0, depends on your implementation, but I want 0 here. Okay, so why you want to know? You see the our calculations. Once you do addition, you get 1101, correct? 1101. After that, so you want to shift it. That means here you want to make a space, correct? In that space you are imagining 0, correct? That's why this is that place, and here we have to imagine 0. You don't want 1 here. Do you want 1 here? If you want 1 here, then we have to implement shift such a way that the last bit should be added with 1, right? So at this moment shift is done. Slowly we'll understand. Now immediately once shift is done, then again we have to see the bit, this bit. What is this bit? So, and remember one thing, this 1101 are the contents of this one now. So no more we have 1011, that is disappeared. We got 1101 now. So this bit says that again. So what is the meaning of this one? 1 means add. The decision circuit says add. So let us do again add. So these 4 bits are always attached to adder. Okay, 1101. Then 0 plus 1, 1. 1 plus 0, 1, 1 plus 1, 0, 1 plus 1, 0, then carry 1. So 1 0 0 1 1 is the result that will be replaced. Remember 1 0 0 1 1. Let me add here. So because of add, what is going to happen? 1 here, 0 0 here, 1 1 here, right? Then this is not disturbed. We are blindly copying it. We did not change it. Once addition operation is done, so immediately what we have to do? Shift, because every time we have to do shift for the next operation. See now, let's check after addition what should be the result. You see 1 0 0 1 1 1. See 1 0 0 1 1 1. This is our result. This 101 is actually multiplier, correct? We don't want to take that into consideration. Let us continue this process. See, add, shift, add. Now this is the time to shift. We know how to shift now, right? This 0 comes here. Sir, we are losing this bit. Yes, we should lose it because the work of this 1 is done. Now 0 comes here, this 1 comes here, this 1 comes here, this 1 comes here, this 1 comes here, this 0 comes here, this 0 comes here, this 1 comes here. Now this place will be filled with 0. That is shift operation, right? So once shift is done, next immediately what we have to do? Again same thing. We have to see the next bit. What is that? 0. 0 means what? We have to actually add 4 zeros. When you add 4 zeros, content will not be modified, right? Then why to waste the time? So that's why we don't do addition. Here we can save the time, right? So no add. I can say I write no add. That means there is no operation. Content will be same 0 1 0 0 1 1 1 1 0. Right. Now immediately once no add operation is done, again shift, correct? So let us do the shift again. So how to do shift, you know that, right? Okay, this 1 comes here. Sir, we are losing 0. Yes, slowly you should understand that we lost 1, then this bit, and we are just giving the chance to, extend our result, correct? So slowly our result size will be increased and it will cover 2n bits. End of the day, 1 2 3 4 5 6 7 8, your result is going to occupy 8 bits. That's why we have to give room for it. We are giving it, of course. So at this moment we will be losing this bit. We don't want it. Now see, this E1 will come here, which is result. Now this one will, sorry, this is still multiplier. Now this one, which is part of the result, this one here. Now this one here, right, all ones, followed by this 0 here. Next this 0 here, this one here, and this 0 here, 0 here. Okay. Next, same story. Shift is just now done. Once shift is done, what is the next operation? Again based on this bit. This bit is 1. Then go for addition. Blindly do the addition. What is the multiplier? Multiplicand 1 1 0 1. Add it. 1 0 1 plus 1 0 1 plus 1 0 carries 1. So you got 1 0 0 1. Remember it. Okay. So that is 1 0 0 1. Right. So 1 0 0 1. Let me write because of addition. So this carry comes here, this 4 bit 0 0 0 1 will be occupying here. That is add operation, right? So once add is done, we have to shift. Let me do the shifting. So when you do the shift, we know the idea again, right? Here I am showing. After addition, shift now. So this 1 will go. This is the final bit of our multiplier. So that will go off. This 1 will occupy the last bit, right? So this is our answer, part of the answer. Now this 1 comes here. This 1 comes here. Now this 1 comes here. This 0 comes here. This 0 comes here. This 0 comes here. This 1 comes here, and here you get 0. Now remember one thing, once this entire operation is done, we require 8 bits, right? That 8 bits will be like this, 4 plus 4, 8. So in this 8 bits we are going to see the result. The 1 0 0 4 1s is the final answer, right? So this is what generally happens in sequential multiplier. If you observe the process, it is repetitive process, right? If you understand that one step, you can understand everything. What we have to do every time is, first we have to do addition, right? After that shift, after that addition, after that shift. Especially this addition we have to do only if the bit is 1. If the bit is 0, then we have to do no addition, right? Finally, either we are doing addition operation, otherwise no addition operation. Second thing, doing no addition operation is nothing but skipping that addition, that's it. Now after that, every time we are doing shifting. So shift we are not skipping, but addition sometimes skipping. Additions depend on the number of ones, right? Shifts does not depend on anything, right? So that's why number of shift operations, if you see for this problem, how many times we are doing this operation, it depends on the number of multiplier bits. Since there are 4 multiplier bits, then we will be doing 4 shift operations in this process. How many additions you did? You did 1, 2, 3. 3 additions because there are 3 1 bits. That's it. Okay. Now we'll see the implementation part, like how circuitry can be designed. Okay. So already we have gone through the procedure, so it will be very easy for you to understand this thing. So there will be a control sequencer which is going to control all the sequences, like when to do addition, when to do shifting, everything. So this is the important part. So this control sequencer is going to decide when to add and when to shift. Now we have register A, register Q, and one flip flop called C, and we have one n bit adder and one multiplexer. So why multiplexer is, sometimes we have to add multiplicand, sometimes we should not add anything. That means symbolical I can say that multiplexer should select zeros for addition, right? So that is what should happen. That's why multiplexer is going to decide whether the argument is multiplicand, otherwise zeros, based on the control sequencer decision. So control sequencer is going to control multiplexer. Control sequencer says that my dear mux, this time multiplicand, my dear mux, this time zeros. In that way, so multiplexer is controlled by control sequencer. That's why add or no add control will be having by this control sequencer. Second thing, one more thing it is going to have is shift operation. So control sequencer decides when to do shift, and whenever this control sequencer wants to do shift, immediately, so see the diagram. So there will be a right shift like this. C will be moved here. Okay. So maybe control sequencer sends 0 here, this bit to here, this bit to here, in that way. So these registers are connected. Okay. So we are just seeing the block diagram, not exact circuit details, correct? So that is not relevant, unnecessary, right? If you understand this level, that is sufficient, right? While really designing something, we will go to low level details, like now adder. So how to design adder we will see, and how this shift register will work, everything will see. But at this moment you should know that shift register will move the bits like this, I mean right side, left side, depends on the kind of shift you are using. So now what happens is, this bit will be seen by your control sequencer. If this bit is 1, then immediately this control sequencer will enable this multiplexer. That means, so your control sequencer is going to tell mux that, my dear mux, please send multiplicand to that adder. Then in the next cycle, probably that n bit adder will add this one, and it is connected to one more thing, right? You know that, of course. So this adder is connected to multiplicand and this temporary register, right? Like this. So always addition will take place here. Now after that carry will come, that carry will go here. Then immediately what happens? This shift operation will take place. That's why such a way control sequencer will be designed. So this is the idea. Okay. So now we have seen array multiplier and sequential multiplier, but we did not discuss about negative numbers, correct? So how negative number multiplication takes place? So we will see that. Okay. So far just our assumption was numbers are positive and we used unsigned number multiplication. Now we are going to use signed number multiplication. That means what are the precautions we have to take, that means what are the corrections we have to make, so that multiplications works for negative numbers also, we have to take care. Now I will explain that. So far we have seen multiplication of unsigned numbers, right? Now what about signed numbers? How to extend this concept to signed numbers is a question. Don't worry, whatever you have learned so far about multiplication of unsigned numbers, that we can use by modifying little bit. Okay, we will see that. Before going to complete idea, first of all I would like to solve a simpler problem, that is, what about multiplication of negative number and positive number? Okay, now we are taking a case where we are multiplying one negative number, second one positive number. Okay, first we see that. So after that we extend it to all possibilities. That's why I have taken 1101, which is negative number. So why it is negative? It is also positive, sir. No, it is not positive. It depends on how you view it. Correct? If you assume that it is positive number, it is positive and value is 13. That means you are using unsigned representation. But if you want to say that this is negative number, if you want to assume it as negative number, then we have to use sign number representations, correct? It's all about how you represent it. Now let me assume that my representation is 2's complement representation. In 2's complement representation, what is 1101? It is minus 8 plus 4 plus 1 minus 3, isn't it? Now 0111 is nothing but 7. Now we are first covering a case where the multiplicand is negative, multiplier is positive. Now we pretend like we are doing unsigned number multiplication, and we will see why it won't work. So 1 0 1 1 first, right? 1101. Next, now again we multiply with this one. So far just we'll cross check whether it is correct or not. So overall result should be minus 21. At this moment, the first bit, forget about all these 3 bits. Since you are multiplying with the first bit, value wise it is 1, right? It is like 1, right? So you are multiplying with 1. 1 into 1101, 1 into minus 3, minus 3. Yes, it is minus 3. Perfect. So up to this point it is correct. Now let's extend our idea. We are multiplying with this one, right? Let us do that. 1 0 1 1. You get 1101. Let's check again. 1 1 1 1 plus 1 0 1 1 plus 1 0 1. So this is the result of multiplying 1101 with 1 1, right? So I am assuming that this is positive number, right? 3. So this is negative number, minus 3. Minus 3 into 3 what? Minus 9, right? So I should get minus 9, but what is the result you got, you see, so far? 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, it is 32. This is, minus 32 plus, what is this one? 4, this is 2, this is 1, right? So minus 32 plus 7, minus 25. So I am getting result as minus 25. But I supposed to get a result of minus 9. Why I didn't get? I will tell you the reason. The mistake what you are doing is, so you are assuming unsigned number multiplication in that we use here 0, correct? So you are adding 0 plus 1 which is 0. But actually really you are you want to say that this is a negative number. What is 1101? A negative number. When it is negative number, then you should not add 0 here, right? So that's why this should be 1, because you want to say that this number is minus 3. But if you write 0 here, then 01101 is not minus 3, right? So that's why the sign extension comes in the picture. This is supposed to be 1. Now if I write 1101 instead of 1101, both are same, you see, correct? So that's why always you remember, whenever you shift this one to right, then we have to add 1 rather than 0, because now it is signed multiplication. So when multiplicand is negative number, then what you have to do? You have to extend the sign bit. So this idea is now simple from now onwards. Check it out. First of all, your multiplicand. If your multiplicand is negative, then simply add 1. If your multiplicand is positive number, continue like unsigned number multiplication. There will not be any problem, right? We have seen it already. Let's check it out. 0 1 1 1 1 1 1 plus 1 0 1 1 plus 1 plus 1 1. You get here 1, and you get here 1. Let us cross check whether it is correct or not. So far what I did is, I did minus 3 into this plus 3. Minus 3 into 3 is what? Minus 9, correct? So is it minus 9 or not? We will see. So minus 2 power, this is 6 I think, right? This is minus, plus 2 power 5. You know 2's complement conversion, right? Given a 2's complement number, what is the decimal equivalent? Minus 2 power 6 plus 2 power 5. This is 2 power 4, 2 cube, 2 square, 2 power 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, minus 2 power 5. So minus 32 plus 16 plus this one 4 plus 2 plus 1 7. So minus 32 plus 23, which is minus 9. Perfect. So finally what I want to tell you is, when you take multiplicand as negative number, one extra step we have to do so that you get the correct answer is, we should, while shifting right side, we have to extend. That means the bit, the last bit, carry bit, you remember that carry bit should be, should get 1. That is one thing. This is called sign extension. So extend the sign simply. Second thing, everything is correct. Simply do unsigned number addition. It will work for signed number also. So far I got minus 9. Let me continue. So I use now this, I am going to use this bit now. So 1, that means 1101. Let us add 1101 where? Here, right? So 1101. Let's try. Now it is a negative number, and that means some 2's complement numbers, right? When you have two 2's complement numbers, of course negative numbers, they how to do their addition? Did you remember? In 2's complement addition, negative numbers or positive numbers, addition technique is very simple. Just add them. 1, 1. Add like two binary numbers. 1 plus 1, 0. You get 1. And 1 plus 1, 0. 1. 1 plus 1 plus 1, 1. Right? Carry 1. Now you get 110101, right? So this is about addition, right? This definitely works. If you want to know, you just cross check. So far what you did is you multiplied 1101 with triple one. Triple one is 7, right? Overall it's a positive number. What is the weightage up to here? 7. So minus 3 into 7, it's supposed to be minus 21, right? Is it minus 21 or not? We will check. So 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5. According to sign extension, this bit is not required, correct? So 110111 is equivalent to 101011. Let us see the value. 2 power 0, 2 1, 2 square, 2 cube, 2 power 4, 2 power 5. Minus 32 plus, this is weightage 8, this is 2, this is 1. Minus 32 plus 11, minus 21. Perfect. So finally what I want to tell you is, your simple unsigned number addition, this one. I did not do anything. But only thing is, when you have negative number, then as a multiplicand and positive number as multiplier, then we have to extend sign bit. So now let us understand what we understood so far. First of all, we took two unsigned numbers, correct? So when we have two unsigned numbers, then we know how to multiply them, right? Now when it comes to signed numbers, let us talk about now signed numbers. Signed numbers can be classified into 4 parts. So when the numbers are signed, maybe it can happen like, the numbers currently when what you are multiplying are positive, right? Or otherwise non-negative, okay? Non-negative. If they are non-negative, like 0, 1, 0, 1, 0, then you can multiply like the unsigned numbers. Already you have a logic for unsigned numbers. You use that logic. Yes. So we don't have any problem when multiplying to non-negative numbers. What if one is negative, okay, and one is positive, okay, or non-negative? Let us take one negative, second non-negative, this case. In that case, idea again same like unsigned number multiplication. Only thing we have to do is you have to use a trick called sign extension, correct? While shifting we have to do sign extension. That's it. Sir, there is one more case. What is that? What if your multiplier is non-negative, sorry, multiplicand is non-negative and multiplier is negative? So how you solve this problem, sir? I will tell you. Example, what do you want to say? Sir, multiplication of 3 into minus 7. How you work it out? Will it work? So definitely it won't work. You just check it out. For that what we do is we play a trick. So we take 2's complement of 3. Okay. If I take 2's complement of 3, that is minus 3, correct? In our 2's complement representations. So here one thing you remember, this entire story I am teaching for 2's complement representations. Okay. Generally how you take when you have sign numbers, how you represent them? 2's complement, right? If it is 2's complement, when you have example 3, that means what are you going to have? If I am taking 4 bits, 0 0 1 1. Okay. So whenever you have 0 0 1 1, the first step what you do is take minus 3. I will tell you how to take minus 3. Forget about patterns. First come to just simple numbers. When you want to do 3 into minus 7, what you do is take negative version of 3, that means minus 3. Take negative version of minus 7, that is 7. So apply multiplication. Minus 3 into 7, minus 21. 3 into minus 7, minus 21. If I apply negative to these two, are you altering the answer? No, you get same answer. Sir, but why are you doing that? So I will tell you. Already you have studied how to multiply a negative multiplicand with a positive multiplier, correct? Negative multiplicand, positive multiplier, or non-negative multiplier. So in that already you have logic. Same thing you can use, correct? So this case is covered, this case is covered, this case is covered now. When you have non-negative and negative, first convert them to negative and non-negative. Sir, but still you have not covered another case. What is that? What if I have numbers negative and negative? What are you going to do? Simple. When I have two negative numbers to multiply, like minus 3 into minus 7, then I take their positive versions. That means minus of minus 3 I do, plus 3, minus of minus 7, 7. Now these two are positive numbers. Positive number multiplication is exactly like unsigned number multiplication, right? Example, someone asks how to multiply 0, 11, 0, 11. I have a logic, right? Same like, but sign extension we have to do. That means, so rather than writing ones in the empty places, we should write zeros. That already we have seen, correct? Recall. How did you do it? So 0, 1, 1 into 0, 1, 1. First we did 0, 1, 1, right? 1 into 1, 1, 1 into 1, 1, 1 into 0, 0. Okay. Then next time. 1 into 1, 1 into 1, 1 into 0, 0. Did you remember? So this place to be assumed what? 1 or 0? 0. So it depends on this remaining bit. So if this bit is 0, we have to add 0. If this bit is 1, we have to add 1. So that positive case can be covered. Non-negative case can be covered, right? Only because of this sign extension. Now the remaining two cases are just we have discussed. One is non-negative, negative. Whenever you have non-negative, negative, simply convert them to, just negate them. That's it. How to negate them I will tell you. Example, you have 3 into minus 7 and you want to multiply. That means multiplier is negative, multiplicand is positive. So that means you have 3 in the 2's complement means what? You have 0, 0, 1, 1. You have minus 7 means what? 1, 0, 0, 1. This is minus 7. Okay, 2's complement representations. But you know how to multiply minus 3 into 7, isn't it? Yes, one negative, one positive, you know how to do, right? So that's why what you do is simply apply 2's complement to 0, 0, 1, 1. 2's complement we know, right? Bitwise complementation 1, 1, 0, 0. We need a special circuit for that, right? It's not a big deal. Just bitwise complementation is not a big deal. After that, add plus 1. Then you get what? 1, 0, 1, 1, 1, 1, 0, 1. 1, 1, 0, 1 is nothing but minus 8. See, already we know minus 3, correct? So here what are we going to do? We are applying 2's complement. Next, apply 2's complement here. Then you get what? 0, 1, 1, 0 followed by plus 1. So 1, 1, 1, 0. 0, triple 1. So we are going to get positive version of minus 7, that is plus 7. Once you have these two, then you do multiplication. Already we have discussed how to apply multiplication between minus multiplicand and positive multiplier. So once you get the answer that is equivalent to original answer, right? That means expected answer. So the reason is, we know one thing, a into minus b is equivalent to minus a into b. But we know how to do minus a into b. But I don't know how to do a into minus b. That's why we are using minus a into b, because the result is same. So in that way we can cover non-negative and negative. So the last case, sir, how you cover negative and negative? That means multiplier, multiplicand, both are negative. So that is very simple. If you have minus 3 into minus 7, then again take positive versions. Minus 3 into minus 7 is equivalent to 3 into 7. But we know how to multiply 3 into 7, right? Same story. So finally all the cases can be covered only if you do sign extension, correct? So now we will see with one example. So the circuit whatever I taught already, right? So already I explained you circuit. That means otherwise I can say it's not exactly circuit, the block diagram, right? The block diagram for the functionality of your multiplication, unsigned number multiplication. A small correction, only small correction we have to do is in the carry bit. In the carry bit, rather than sending 0 while shifting, it should depend on the number. If it is a negative number, multiplicand is negative number, send 1. Multiplicand is positive number, then send 0. Such a way if you plan the circuit, everything will work. Now, so finally if you add that step, then why we can cover all that cases just now we have seen, correct? So that works for positive, because when the numbers are positive, then we will be sending as it is, like we will be extending sign. So sign extension means if its number is already positive, then we are adding 0. That means we are shifting 0. Then if it is already negative, then we are shifting 1. If you do that, definitely multiplications will work for these two cases. Remaining two cases are simply these two cases if you do 2's complementation, correct? Now this is about multiplication of signed numbers. There is no much difference. I hope you understood, but I would like to summarize it. Okay, let's summarize it. Let us summarize this multiplication idea with some example. Let's say you want to multiply 1101 with 1101. Okay, how this machine is going to work? First of all, you remember this is specially designed for multiplying, two non-negative numbers. Second thing, multiplicand negative, multiplier positive, right? So that two cases it will cover this machine. But negative negative, second one, anything, positive negative. So that cases we have to cover. How we are going to cover that two cases I will tell you. So first of all, what happens, this circuit you understood now. It is like unsigned multiplication circuit, but only thing is this, while shifting, this bit is updated by either 0 1 depends on the multiplicand. If multiplicand is negative, then this bit will be 1. Multiplicand is positive, then we will be adding 0 here while shifting. Okay, so if you do that, that process is called sign extension. That means if you have 1101 while shifting, so here you always get 1, right? That is what? If it is positive number, then we are going to get 0. Such a way we can plan our circuit. Assume that we have such design now. So if you want to multiply 1101 negative case, right, then there will be a small circuit that will detect that it is a negative case. Whenever it is negative case, so directly we have, let's say, big circuit here. Okay, so this big circuit can multiply positive, otherwise I can say like this, non-negative, correct? Sorry, yeah, non-negative case we can multiply. Second case what we have seen, negative, but multiplier is non-negative. This case also we can cover using this circuit. Such circuit we have, but we don't have a circuit for negative. Then what to do? Then so there will be a small circuit, okay, that can detect these two bits, like 1 1. Whenever these two bits are 1 1, then that circuit is applying 2's complement for 1101, 2's complement to 1101. We are changing the sign. Okay, so 1101's 2's complement is what? Definitely 0010 plus 1. It would be 1100 So this 1101 will be replaced with 0011. Such a extra circuit you should have. It's not a big deal when you are designing computer organization, very big computer, then definitely this kind of small circuits is not a big deal to design for us. Second thing, here also 1101 should be 2's complemented, then you get what? Same 0011, same process. Once it is done, now we know the story. It's as it is. Now already this machine can be this machine can work for non-negative and negative, right? There will not be any problem. Happily you get the exact correct answer, right? So 0011 is 3, 0011 is 3. Really, if this machine works, it gives you 9, but minus 3 into minus 3 also plus 9, that's why. So there is no problem in that way. So we can design a circuit for multiplication of any numbers. So finally we covered multiplication of signed numbers, right? Signed numbers. That's why. Sir, why you taught us multiplication of unsigned numbers? So when you learn multiplication of unsigned numbers, then so learning signed number multiplication would become easy, right? That is what our goal. That's why slowly we are learning. First of all, basic ideas. After that, we are extending the ideas. That will be the best way of learning anything. Otherwise, I can directly teach you signed number multiplication and I can tell everything in 5 minutes. Not a big deal. See, end of the day, the climax part is very easy to, climax part is the essential thing, right? But to achieve to climax, we have to develop logics, right? That means you have to understand reasoning. So without reasoning, if I directly teach like this, you have a circuit and blindly do sign extension without telling the reasons, definitely the class will be definitely I can say fruitless. That means you don't get any benefits from that. You understand solutions, how to multiply two numbers, you understand, but you don't know the reason why we are doing all this stuff. Why I am shifting 1 here? If I blindly say you shift 1 for negative numbers, but if I don't give you the reason, then that kind of study will be unnecessary, and if they give very difficult gate questions, you cannot solve, right? So that's why you remember we will be studying from basics, and we will be covering advanced things. Example, I covered array multiplier, but I took 1 hour of time to teach you array multiplier, but that same thing can be taught in 5 minutes. Okay, directly I can take a circuit and I can explain this is what happening. But I'm not doing that. What I'm doing is I'm just starting from reasoning, like why, what is the motive behind designing such kind of big circuit, how they people started designing that kind of circuits. For that, what was what was the idea running on their brains, that we are understanding. Okay, so similarly here also same thing. So my computer organization classes will be lengthy, but go through them. Okay, so if you go through them, definitely you will be getting best marks in computer organization. Okay.